Getting all set up here. Well, let's get started. So I want to just let you all know the official date of the second test here. So let me just put that in the conversation here. So test 2 is on Wednesday, not this Wednesday, Wednesday 10/28. So I just put that in the chat. That's just, I believe that's 2 weeks from this Wednesday. So you've got a little over 2 weeks. I didn't want to make it the week of fall break on that Wednesday, so I made it the Wednesday after that. Any questions about test 2? It'll be very similar to test 1 in terms of how it works, where I take and look at the quizzes that you've had and the problems I put in the quizzes and pick some of those to put on the test and so forth, like that. Anybody have any questions about test 2 at this point? We will talk about it later. I just wanted to make sure we get that on yours and my schedule. So we are going to switch gears today and talk about what the first and second derivative tells us about the graph of the original function. So let's get started. I'm first going to go over a document here, a one-page document, just to give you some idea of what we're talking about. Feel free to ask questions. So let's start at the top. I've got a couple graphs here. Let's take a look at those graphs, and these are graphs of original functions. You will notice that if I come in from left to right, you will notice that this graph here is going down, 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 down. So I'm coming in from left to right. This graph is going down, 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 down. That means it's decreasing there. In other words, the y coordinates are getting smaller and smaller until we get to this point right here, wherever that happens to be. And then the y values start increasing again. And that's the reason for this increasing symbol right here. So what happened at the C, at this point C here? There's a change from decreasing to increasing. There's a low point on the graph in a small region of the graph. There's what we call a relative minimum there. There's a relative minimum at C. So, as well as, what's the tangent line at C look like? Now remember, the first derivative is the slope of the tangent line. A tangent line to a particular point on a graph is the straight line that best approximates the graph on both sides of the graph, and it's the unique line that does so. Now we'll talk about what these C's are in a minute. I've labeled those with C's. Let's look over at this graph now. This graph, if you're coming in from left, if you're going from left to right, first the y values are going up, so it's increasing. And then at this point right up here, the y values start to go down. So that's on this part of the graph right here, it's decreasing. Now what happens up here? What happens up here at this particular point? That's a sharp corner. So there is not, remember, there's no unique tangent lines at sharp corners. The graphs are not differentiable at sharp corners like that. So that's what I want to point out here. But we still are calling this C for this, the X coordinate of this point, we're still calling C for a reason, which we'll talk about. So let's take a look at what these C's are actually called critical numbers. C for critical numbers. These critical numbers play a very important role in calculus. So let's look at this particular point, this particular critical point, we could call it, which has an X coordinate and a Y coordinate. Critical numbers is just reserved for the X coordinates. So let's look at this critical number here for a moment. Here's our tangent line that we drew. The slope of that tangent line is the first derivative. So the first derivative at this C is the slope of this tangent line. This tangent line is horizontal, and horizontal lines have a slope of 0. So let me just say that again. The first derivative is the slope of the tangent line. The first derivative at a point, any point C or X or whatever you're calling it, that first derivative is the slope of the tangent line. Here's the tangent line that I drew in. Since it's horizontal, its slope is 0 because the y's are not changing. The y's are always the same number on this line, and they are not changing at all. And slope is change in y over change in x, so the y, there's 0 change in the y. So 0's in the numerator, and that makes the slope of this tangent line 0. Remember, the first derivative is the slope of the tangent line, and it is 0. So at C here is in this graph, or in this diagram, if you will. At C, the first derivative is 0. That's very important because it turns out that where the first derivative is 0, that particular value of C is a candidate for a relative extreme point. A relative extreme point is a point like this. It's a low point on a graph in a small region, or a high point on a graph in a small region. So we'll get to that more in a bit. Over here, what we see is we see up here the first derivative at C here. Remember, the tangent line does not exist. So the first derivative at C does not exist. There's no way to draw a tangent line here because it's a corner. I could draw it here, but then it wouldn't be approximating the graph on the other side. I could draw it here, but then it wouldn't be approximating the graph on the other side. So there's no way to draw it. And if at any time, if you have any questions and you're not understanding, please let me know. So let's talk more about critical numbers. The critical numbers for a function f are, I've got it twice, those numbers C in the domain of f. Yes, those numbers C, whatever we're talking about here, must be in the domain of the original function. In other words, you must be able to put those C's in your original function and come out with an answer. And the critical numbers for function f are those numbers c in the domain of f for which the first derivative is 0 or the first derivative does not exist. Why do we look at those? Why do we have those particular conditions? Because what we're looking for is we're looking for a way to precisely find these points. This point right here and this point right here. That's what we're looking for. And we want to be able to find both coordinates of those points. So if you notice when we go down here and then we turn in a small region of the graph, this point that we're calling C is a low point. It's called a relative minimum over here, relative minimum. And in a small region of this graph, this is a high point. We're calling that a relative maximum. This C, comma, f of C is a high point of the graph. So we're calling that a relative maximum. So together, these two right here are called relative extrema. So these two guys right here, oops, didn't mean to do that, but sometimes that happens. These guys are called relative extrema. And let me go put that back on. And I'll just use the shorthand, relative I'll use REL for short, extrema. I'm just trying to get you extreme up. So EXTR. I think I need a T in there. Extrema. So EXTR EMA. Whoops. Let me try to recenter myself again. I'll just try it one more time. That software kind of, I think I don't want that. Extrema. So that would be EXTREMA. Okay, so I want you to know that those two together are considered to be relative extrema. Whether relative extrema consists of relative minimums and relative maximums. Or you could say relative minima is the plural of relative minimum, and relative maxima is the plural of relative maximum. This is a low point, this is a high point, and together we call them relative extrema. Why do we study relative extrema? Okay. Or why do we look at critical numbers? We look at critical numbers. Why do we look at these? We look at critical numbers because they are the only candidates for relative extreme points, relative extrema. That's why we look at critical numbers. And we can see that the C here is a low point and the C here is a high point. And extreme points mean low points in a small region of the graph and high points in a small region of the graph. So we study critical numbers because they are the only candidates for relative extrema. And they're important because they're turning points. This one is, this graph is decreasing on this side and then it turns and becomes increasing on this side. And this is the opposite. It's increasing on this side, and then up here at this point turns and is decreasing on this side. So it's important to know where those peaks or valleys are on the graph and to know them precisely. So what's our goal here? We want to use calculus to find intervals on which f of x is increasing and intervals on which f of x is decreasing. So we're looking for where it's increasing or decreasing. Why do we want to know that? We want to know it, and we want to know it precisely. That's the beauty of the calculus. We want to know it precisely. So what does that tell us? Okay, these critical numbers are the only candidates for relative extrema. And what we're going to do is we're going to create a first derivative sign chart to give us this information. So we've got our candidates for relative extreme points, but that doesn't mean that each critical number is going to result in a relative extreme point. So just so you know. So they're just candidates for relative extrema. Critical numbers are candidates for relative extrema. So we want to use calculus to find the intervals and we're going to use the first derivative to do so. We're going to use the first derivative here. And that first derivative is going to give us information about where the original function is increasing and intervals where the original function is decreasing. And how do we, from college algebra days, how do we identify relative extreme points? Well, that's where you've got either a change from decreasing to increasing or increasing to decreasing. So on a test, you will be required to give a completed first derivative sign chart and table. We will talk about those and do some particular problems today so you can see what I'm looking for. So I'm not just looking for the answer. I'm not just looking for you to draw a graph with your calculator and identify from the graph. I want to see the calculus, and that includes the first derivative sign chart and the table. So this is right here, the first derivative sign chart. That's what I'm calling the sign chart. Here is what I'm calling the table. This will make more sense after we problems. This is the table. You want a column for the interval, you want a column for the test point, and you want a column for the sign of the first derivative. And that information we are then going to use to fill out the sign chart up here. And be sure to show justification for each sign. Anybody have any questions on this particular page? I will put this in your course just as soon, probably around noon today after I finish teaching my trig class, which is after this class. Any questions? So let's take a look at the homework. It is a jam-packed homework. If you can see there are 18 pages. I'm so glad that my new flatbed scanner came and I set it up on Saturday so I could have access to it. I did not like using my phone to take pictures of my work so I could present it in class. That's okay maybe for a few pages, but it's not the clear black and white I was looking for. So I'm just really happy it came and it worked like a charm. Didn't take me long to set it up. So I've got some questions in this assignment that I want to go over with you. Before I go over those problems with you. I do want to mention something. Let me go into Canvas for a moment. I sent you all a email through Canvas. It's constructing the unit circle from scratch. I had an opportunity to visit with one of the students, and I worked with her to construct the unit circle from scratch. It will deepen your understanding of trig so much. What's different about trig than other math classes that you've taken so far is if you try to memorize everything in trig, I can almost guarantee you by the time the comprehensive final rolls around, you're going to forget something. There's just too much. So one of the items that I'm trying to encourage students to do is to construct the unit circle from scratch. I do not have time to go over this in this course, as this course is the most jam-packed course that I've ever taught at NWAC in terms of what it covers. So what I did is I made a video of my session with this student on Friday, and I've included that YouTube link in this particular email for you. And here's the blank unit circle. Very important to be able to do that. It will show you whether you understand reference angles and whether you understand the unit circle, and you can literally create the unit circle from the ground up. So what this is a blank unit circle like that. And just to give you a little taste of it, you start by putting in the degrees. So this is for degrees, this is for radians, this is for the x, this is for the y coordinate. Remember, on the unit circle, r is 1 when we're talking unit circle. So now, what degrees do we put in here? Well, you remember our special triangles. What did we have? In those special triangles, we had 30 degrees. And in another one, we had 45 degrees. In the first one, we had 60 degrees. That's what goes here. And of course, 90 degrees goes up here. Okay, 90 degrees goes up here, right there, in that blank right there. So after that, you're just using reference. You're using these same angles, and you're using reference angles. Keeping in mind reference angles to fill out the rest of the degrees around the circle. Well, we know how to convert degrees to radians, and you just convert all of those to radians. You just take and multiply by pi over 180. And once you have those, you can find out what the x and y's are for each one of these. And the x is cosine and the y is sine. So it's not really difficult. And you can do that by using properties, your special triangles, and also knowing what sine and cosine are in terms of those special triangles. So you want to be able to complete this from scratch. You will actually learn a lot, I feel, when you do that. Oh my gosh, did I get the wrong class? I'm so sorry. I don't know what I was thinking. I was thinking about sorry about that. I just realized I thought I was teaching my trig class. But anyway, I sent it to my trig class, not to y'all. I bet you all were like thinking, oh, well, what's going on here? Sorry about that. I was so excited about knowing how to do that from scratch. Sorry. So let's go on. Please stop me if I ever do anything like that again. So let me go back down here. I got to recenter myself. Just so much to think about. So let's take a look at these problems here. And I've got several of these problems that I want to look at. I do not want to look at number 1. I want to look at number 2 here. So we're given a graph. We're wanting to identify the graph g of x, which meets these conditions. And we have there's really 4 choices, but the way MyLab Math prints out these problems, they don't put all 4 choices on there. There's a problem with how their software works, because I don't see this in any other software or any other. I haven't seen in any other software. So let's take a look at this and let's see. So we're talking about, these are the graphs, all possible answers for this graph that we're trying to find. We're trying to decide which one of these represents the graph of g of x here. So g of x is decreasing from negative infinity to negative 6. So from left to right, we're going left to right. Decreasing means going down. And also decreasing from 8 to infinity. And g of x is increasing over this interval, negative 6 to 8. That means it's going up like this. Decreasing from left to right means going down. Increasing means going up from left to right. So this one is decreasing from negative infinity to negative 6. And then at negative 6, it starts increasing all the way to 8. And then at 8, but not including 8, because open parentheses, these parentheses means the endpoint is not included. At 8, it's decreasing again. So we're going decreasing, increasing, decreasing. Well, the only one of these that's decreasing, then decreasing to this relative minimum, and then increasing to this relative maximum, and then decreasing is graph number C. So, or graph letter C. Anybody have any questions on that? So we're just looking at the original graph now to get a feel for what we're looking at, or how do we identify decreasing and increasing and so forth. But what we're really looking for is where a graph is increasing, decreasing, where we've got a relative minimum, a relative maximum, and we want to be able to answer those questions precisely. Please stop me if you have any questions at all. Let's take a look at number 3. So what are we doing here? Now, this is a different type of problem. This is decreasing and increasing. In number 3, we want to draw a graph to match the description given. G of x has a positive derivative over negative infinity to 1, not including 1, and a negative derivative over the interval 1 to infinity. So this is all the numbers between negative infinity all the way to 1, not including 1. These are all the numbers from 1, not including 1, all the way out forever and ever and ever and ever. And we're looking at, on this original function has a positive derivative over this interval and a negative derivative over this interval. Now let's take a look here. So I want to show you why the answer is this one. It's actually D. Just so you understand, we want it to have a positive derivative over negative infinity 1 and a negative derivative over 1 to infinity. And does it or does it not, and why? So what I did is I took this little snippet out here, this graph out here. I moved it over to a sticky note over here. And then I'm thinking, well, graphically, what is the interpretation of the derivative? And graphically, the first derivative means the slope of the tangent line. So I took this graph and I copied it over here and I started drawing tangent lines. Remember, the tangent line at a point is the unique straight line that approximates the curve on both sides of the point. So if I drew the tangent line right at this point right here, it would look something like that. It approximates the curve on both sides of the point. If I drew the tangent line at this point here, it would look something like that. And of course, go on forever and ever. It just would clutter up the graph if I did that. Now, are these positive sloping lines or negative sloping lines? Their slope, the slope of this line is positive because it's going up from left to right. The slope of this line is positive because it's going up. The y values are going up from left to right. The slope is positive. If we look on this side of this relative maximum here, we will see, we will draw a tangent line. I do a tangent line here and here. You would notice that these are going down from left to right. Their slopes turn out to be negative. If you pick 2 points on each line and calculated the slopes would be negative. So what does that mean? If the slopes are positive, slopes of tangent lines, the first derivative is the slope of the tangent line. So I wrote down first derivative over here. So on this side, the first derivative for all these points here, the first derivative is positive. On this side over here, the first derivative is, for all those points over here, the first derivative is negative because the first derivative is the slope of the tangent line and the slopes are negative. So it's important to understand that connection there. So where does that happen? That happens, we want to make sure we're looking at what we're trying to find here. Draw a graph to match the description. G of x has a positive derivative over negative infinity to 1. That would be positive. That's negative infinity to 1 is right here. That's where the derivatives are positive. And then here, a negative derivative over 1 to infinity. Negative derivative on this side, 1 to infinity. That's where those derivatives are negative. So 1 to infinity. So this is the graph that we wanted to choose. Any questions on this? So let's take a look at number 5. So this is an important problem, and you probably want to copy down what I'm expecting to see when you do one of these problems. So on a test, you're required to give a completed first derivative sign chart and table. This is the sign chart right here. This is the table. And to remember to show justification for each sign, which we're going to do. So I'll give you a couple minutes to copy that down so you can follow along with what we're doing as I present some problems. And this is very detailed. There are lots of little steps. So it's going to maybe seem a bit overwhelming at first, but once you start to work some of the problems, I think it'll become second nature to you. So the first one I want to take a look at is number 5. If you need more time, please let me know. So we'll go back to the homework here and take a look at number 5. So number 5 says find in part A any critical values, and in part B any relative extrema. So I'm going to go down to the bottom. I'm going to copy. You probably want to copy down the function just to make sure. I'm pretty sure I copied it down below, but I'm going to copy it down just in case. Okay. Yes, I guess I didn't copy it down. So I did copy down, however, just a reminder as what a critical number is. C is a critical number if f of C exists. And in other words, you have to be able to, whatever your C is, you've got to be able to plug it into the original function and get out a. So this means the y value of the f function at C. So you want to be able to get out a y value. If you can't find it because it, say, gives division by 0, then that C is not a critical number. It has to make, you have to be able to get a y, plug it into your original function and be able to get a y coordinate. And the first derivative at that critical number is 0, or the first derivative at that critical number does not exist. So we want to look for the critical number, and the reason why we look at critical numbers because we're looking for relative extrema, and critical numbers are the only candidates for relative extrema. There's no guarantee, though, that you're going to have a relative extreme point. They're just candidates. So that's why we look at critical numbers, because they are the only candidates for relative extreme points. So it's just sending me notifications. I need to try to figure out how to turn that off. So the first thing we are going to do is take the derivative. In order to find the critical numbers, we've got to take the derivative. So the derivative of this is 2x minus 2. 2x minus 2. So I wrote that down as f prime of x is 2x minus 2. Now we have a potential does not exist right here, but we're talking about a linear function. It always is defined. So we want to find, so we're only talking about having to set this equal to 0, since it's always defined. So I'm going to take this 2x minus 2 and set it equal to 0. Solve for x. So first I'm going to move this minus 2 over to this side. It'll turn out to be plus 2 on this side, equals 2x. And then if we solve for x, we can do so by dividing both sides by 2. 2 divided by 2 is 1. And then 2 divided by 2 here is 1 times x is x. So we get x is equal to 1. That's our only critical number. So we have a critical number here. So this is our critical number. Just to be clear, that's our critical number, 1. So if you notice, I've got a sign chart right here. And I've got a table right here underneath it. I do require you to show me these on a test. I'm looking to see if you understand the process of setting up a chart and a table. Not looking for the answers so much. I'm looking for the process. So I pick problems for students to show me the process. So the first thing I'm going to do is take my critical number and plot it. on this number line here. And at this stage, you're not going to have anything else in here except this chart is really a first derivative. What we are putting on this graph is what's going on where with the first derivative. Right here, we found out that the first derivative, we found the first derivative. And it is 0 at x equals 1. So I put it on the x-axis because that's where it's 0. But it's the x-axis for the first derivative. So now to have the ability to fill this out, I mean, you can put in negative infinity and infinity here. To be able to fill this out in here, we really need to create a table. So in that table, you want the interval. So this is the interval that you're talking about right here, the interval. And I'm just going to call it inter for short. That's your interval that we're talking about. Okay, it's the interval. It's what was up here, the interval, the test point, the sign of the first derivative. So our intervals, if you notice, so you've got this negative infinity here, you've got the 1 here, you've got this positive infinity. So if you notice, you've got one interval from negative infinity to this 1. That's what's here. You've got another interval, and this 1 didn't show up very well here. So let me kind of make sure you know this is a 1. And you've got this other interval that starts a hair past 1 and goes all the way to infinity. Parentheses mean that the endpoints are not included. So we have our two intervals that we need to talk about. This one critical number that we got just broke this x-axis here into two separate intervals, one from negative infinity to positive 1, and the other from positive 1 to infinity, not including 1. We don't want to include it because that's a critical number. So the next step after that is to find a test point. It's an x-coordinate. It turns out that if I pick any x in this interval, these are the x's. If I pick any x in this interval, and I find the sign of the first derivative at that particular value of x, no matter which number I would use in this interval, they would all either turn out to be positive or all turn out to be negative. And in this other interval from 1 to infinity, let's pick 2. Can't pick 1 because it's not included. Let's pick 2. So those are our test points, and I'm emphasizing they are x coordinates. Now, what are we looking for over here? We're looking for the sign of the first derivative at that particular x. So at x equals 0. And the sign of the first derivative at x equals 2. So what is our first derivative? Our first derivative is 2x minus 2, which is why it's so important to label here. So our first derivative is 2x minus 2. We are going to add the second derivative and what it tells us about graphing right after this particular section. So it's important to have a really good understanding of what's going on. So let's take a look at here and evaluate our test points using the first derivative here. So all you want to do for a problem like this is take this 0 and plug it in for x. That's what it's an x. So you would take this 0 and plug it in for x. That's 2 times 0 minus 2 if you do that. This is 0 minus 2, which gives us a negative 2. So the sign of the first derivative is negative. We just need to know it's negative. We really don't need to know the value. Now this time, let's plug 2 in for x here. We get 2 times 2 minus 2. I wrote it down here, so it's even with this interval. So 2 times 2 minus 2, which is 2 times 2, which is 4 minus 2, which is 2. That turns out to be positive. So now we're going to put our signs in the sign chart here. So over this interval, or you can put them below, it doesn't matter either way, above or below. So corresponding to this interval, we want the sign of the first derivative to be negative. So I put negative over here because this is the interval from negative infinity to 1. So no matter which x's we're talking about, when we find the first derivative over here, we're going to get a negative number. I just care that they're negative right now. And when we put this one in, corresponding to this interval, 1 to infinity is over here. So over there, the sign of the first derivative is always positive. Why do we like that? Because it tells us information about our original graph, where the first derivative, which is the slope of the tangent line, where they are negative, then the graph of the original function is decreasing like this. And where the first derivative is positive, that's where the slopes of the tangent lines are positive. And what that means is that the original graph is increasing, going up. So this means, and in terms of the function, original graph, this means increasing. This means decreasing. This is the original graph here. This f of x here is the original graph. This f of x here. So that's what it tells me. So these red arrows have to do with the original graph. Now, what do they want from us in terms of what do they want us to fill in up here? First of all, the critical numbers. We just found one of them, and it turned out to be this one right here, which is 1, x equals 1. They just want us to put in a 1. What about here? Let's look at what's going on here. This is the graph of our original. This is a quick sketch, by no means accurate at all, of the graph of the original function. So when we're coming in here, we're going down, 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 and then we go up. We have a relative minimum point here. We have a low point of our graph because this lies higher, this lies higher. So we have what we call a relative minimum point. So we have a relative minimum point. The relative minimum point is this. We'll talk about why in a moment. And there are no relative maximum points because we only found a relative minimum point. We don't have something that goes like that. So there's a relative minimum point at 1. And how do we get the y coordinate? They're talking about at this point, what's going on with the graph of the original function? That's what we're concerned with here. That's what we're concerned with here. So the relative minimum point is 1 comma something. How do we get the y coordinate? We're talking about the original function at this point, so we want to go back to the original function to find the y coordinate. So we want to know what happens when x is 1. So we want to know what the y coordinate is when the x coordinate is 1. That means we plug 1 into our original function. So we get 1 going in here, we're squaring it. Minus 2, put in the 1. So minus 2 times 1, we're putting in the 1, this 1 for x here. Minus 2 times 1, plus 3. Copy it over. 1 squared is 1, minus 2 times 1, which is minus 2, plus 3. Figure this out. We've got our positives are 1 plus 3, which is 4, minus 2. 4 minus 2 is 2. That's where this 2 came from. Any questions on our first example here? If you understand that, that's going to go a long way to helping you understand the rest of the problems. It's important to understand a simple one. So I'm just going to make sure that I know the number here because I am crossing it off my list. I'm making sure I note to myself where we are at in terms of time. So let's take a look at number 6. And you can see we're going to have a minimum and a maximum point here, a relative minimum and maximum point here. So we're going to go through the same process. They're really asking us to do the same process. But instead of what we had last time, which, what did we have? We had a quadratic where the highest power is a 2. This time we have a cubic. So let's do this problem and let's differentiate. So we want to find g prime of x to get our candidates for relative extrema. So those candidates are the critical numbers. In order to find the critical numbers, we need to have g prime. So that would be 3x squared minus 27 times the derivative of x, which is 1. So it's 3x squared minus 27. And then the rest, this is the derivative of this term is 0. 3x squared minus 27. So our g prime of x is 3x squared minus 27. That's always defined. You can take any real number, square it, multiply it by 3, and subtract 27. There's never, ever an issue with that. So now we want to find their critical numbers. Since it's always defined, we do not have to consider where the function is undefined. That's another issue that we might have to consider down the road. So since it's always defined, all I have to do is set the function equal to 0. So we're going to take this out, put in 0, and get 3x squared minus 27 is equal to 0. So we want to just solve this for x. Ever how you're comfortable solving it for x. So let's go this direction. I'm going to move this minus 27 over to the other side. That's then going to become positive 27 on this side. Then I want to solve for x. So let's solve for x squared. Let's move this 3, the opposite of multiplication, division. So this 3 is going to end up in the denominator on this side. And the 3's will end up canceling, and we're left with the x squared. 27 divided by 3 is 9, equals just x squared on this side. Now, when with this 2 here, likely means we have 2 different solutions. So you want to take the square root of both sides, but you will need to put the plus or minus with one side or the other. So the square root of 9 is 3. The square root of x squared is x, but we need to put the plus or minus with one of the sides. Since we're solving for x, we want to put the plus or minus with the 3. So we have 2 critical numbers here. Our critical numbers are -3 and +3. Let's see, did they ask for the critical numbers here? -3 and +3. So let's go on. So we have our critical numbers. We want to plot them on a number line. So -3, if you're going from left to right, comes before 3. And you will notice now we have those 2 points have broken this x-axis into 3 intervals. The one from -infinity to -3. The next one from -3 to 3. The last one from 3 to infinity. And I just wrote all of those intervals down. We want to pick a test point, which is an x coordinate in each one of these intervals. It doesn't matter which one you pick in there. All of you could pick a different number. It will still take you to the same place. So in this one, let's go back one. -3 minus 1 is -4, because we're going back towards -infinity. In here, there's a change from negative to positive. That means zeros inside that interval. Here, let's go take 3 and add 1 to get 4. Those are our test points. And then we want to figure out the sign of our first derivative. Our first derivative is 3x squared minus 27. So I just copied that down. So we're going to first put in -4 here. And we can take our calculator. We can put -4 in, negative in the bottom row, and then square it. And after that's squared here, I can multiply that times 3 and then subtract 27. And I get 21. If I were to put 0 in here, 0 squared is 0 times 3 is 0. We get just -27 right here. If I put in 4, well, -4 squared in here, and then +4 squared in there are going to both give us 16. So this answer actually turns out to be the same. But the point is, this 21 is positive. This -27 is negative. This 21 is positive. We're looking for the signs. And I should have marked in the signs here. And let me do that real fast. So we've got plus here, minus, plus. And while I'm here, this is what's going on with the original graph, g of x. What I've drawn below it. And see if I can get this off for a moment. So you can see it all. Oops, this little thing, okay. So we've got this. That's crazy. I don't know why that one. So this one is plus. Now, what I want to do is, what does that mean about the graph of the original function? Close. See if I can do that now. Yes, okay. What does that mean about the graph of the original function? When the first derivative is positive, what does that tell me about the original graph of g of x? It tells me that that's increasing. Tells me that this is increasing. That's what it tells me. And where the derivative is negative, the original graph is decreasing. And where it's positive, where the first derivative is positive, is where the original graph is increasing. So that's what's going on there. So that's what it really looks like. So now we need to answer those questions. We see we've got a change from, this is our original graph, just a quick and dirty sketch. It's telling us we're increasing to -3, then decreasing, but we have a relative maximum here, a high point. We have a high point. So we have a relative maximum point at x equals -3. And over here, we're decreasing and then increasing. We have a low point. We have a relative minimum here. So that's what it's telling us. So we have a relative maximum at -3, and we have a minimum at 3. So let's go back up here and see what we need to do in terms of what we need to fill out. So we've got a relative minimum point at x equals 3. We have a relative maximum point at x equals -3. How do I get these y's that correspond? Go back and we take our x coordinates and we plug it back into the original function. You're going to see this a lot in this course. You want to always get your y values, you plug back into the original function. Any questions on this particular problem? Let's take a look at number 7 here. So here is our function, f of x equals x cubed plus 13x plus 10. So we want to find, it's actually t of x, sorry. It's t of x equals x cubed plus 13x plus 10. We want to find the derivative. 3 comes down, we get 3x. 3 minus 1 is 2, 3x squared plus 13. And that's it, 3x squared plus 13. That's always defined. Let's set it equal to 0. Take out the first derivative notation, put in 0, and let's solve for x. If we solve for x, let's move this 13 to the other side. It will end up as a -13 on the other side, equals 3x squared. Let's divide both sides by 3. So we get -13 divided by 3. These 3's cancel. We get x squared. I put the x squared on this side, equals -13 over 3 on this side. If we take the square root of both sides, we need to put plus or minus with one of the sides. Now what you will notice here is we're taking plus or minus the square root of a negative number. That negative means -1. The square root of -1 is actually the imaginary unit, which is I. We have the imaginary unit to represent complex numbers, but we're only graphing in the real number system. We don't want an I. It's much more difficult to graph in the complex number system. So we're only talking about the real number system here. So this is not real because of this I here. Or you could look at it as the negative. It's a negative inside of the square root. That means it's not real. So as I mentioned, we're graphing only in the real number system. So we want real numbers only. So what is the answer to this problem? The answer to this problem is the function has no critical values. And critical values are the only candidates for relative extrema. They're the only candidates there are for relative extrema. That means we have no And relative extrema are relative minimum points and relative maximum points. That means we don't have any of them. We have no relative minimum points and we have no relative maximum points. So that's kind of an oddball problem, but I did want to go over it. So that's number 7. Let's take a look at number 11. That's 9. I'll make sure these notes are in here for you. Might want to take a look at my instructor resources, especially for this one. And then we want to take a look at negative, or we want to look at positive 11. There's 10. I wrote that. There is 11. So this is a little different of a problem. How do we handle this problem? We go about it exactly the same way. We take the first derivative first. So let me see what I've got down there. Oh, did they not? Maybe they. Yes, I'm on the next page. Okay, let's go to the next page. Here's our original function. We want to find the first derivative. Will we differentiate term by term? That -5 is an additive constant. The derivative is 0. Copy down this negative sign. The 2/3 comes down in front. The simple power rule. The x we copy over. To get the new power, we take the old power and subtract 1. And when we do that, this is 2/3 minus 3/3, which is -1/3. I'm going to put this in the denominator right here. Move it to the denominator. It changes only the sign on the exponent. So -2/3, we've got -2/3 right here. When this goes down to the denominator, the x stays the same, only the sign on the exponent changes, and it will change to +1/3. So remember, critical numbers, going back here, critical numbers are number C, for which the first derivative is 0, or the first derivative does not exist. In this situation that we are in right now, the first derivative does not exist, because what happens if we plug in 0 here? We get 0 to the 1/3, which is 0, times 3 is still 0. Division by 0 is undefined. You could put your favorite number in your calculator, do 2 divided by 0. If the entire denominator is 0, you will get a warning that says attempted calculation contains division by 0. So 0 is the critical number here. And it's the only critical number because there's there's no x's in the numerator to give us a place where the first or to give us some. There are no x's up here. So if you take and you set the numerator equal to 0 to find them, there's no x's you're going to get you're going to get -2 equals 0. Doesn't make any sense. So we're not getting any contribution there. So our only critical number is 0. So I plotted this on a number line. It's actually undefined there because it's division by 0. If I put 0 in here, the entire denominator will be 0. So our first derivative is actually undefined there. We still use the same process. This 0 splits this x-axis, if you will, into 2 separate intervals, -∞ to 0 and 0 to infinity. We still choose a test point in each one of those intervals. If you go back 1 towards -∞, you take 0 minus 1, you're going to get -1, which is what I chose. Here, you can choose 1. And what are we looking for the sign of this time? We're looking for the sign of the entire first derivative, which is -2 over 3 x to the 1/3 in the denominator. That's what we're looking for. So we want to take this -1, plug it in for x. We get -2 up here, 3 times -1 to the 1/3. You can figure out what this is on your calculator. Turns out this encircled part here, -1 to the 1/3, is negative. So I said, okay, there's a negative here, there's a negative here, 2 and 3 are positive, 2 negatives make a positive. So the sign of this right here has to be positive. That was the thinking that I was involved there. But you can fully calculate the whole expression in Math Bracket and see what the sign is. Here, this one isn't too bad. This one isn't too bad. For this interval, we chose 1. Let's plug in 1 up here for x, and we will get -2/3, 1 raised to the 1/3 power. And you can see 1 to any power is 1. So we just have a single negative. So the sign here is going to be negative. We put the +1 up here, and then negative over here. This plus is going to make this go up. The negative is going to make it go down. So we have a relative maximum at 0. So let's go see what they wanted. We have a relative maximum point at 0. We did not find any relative minimum points, so we want this option right here. We want to, and how do we figure this out? Whenever we want a y-coordinate in this class, we take the x-coordinate, plug it into the original function, and you will see that when we plug 0 in here, we're going to get 0 to the 2/3, which is still 0. And so we're going to have -5 minus 0, which is just -5. And they want us also to choose the correct graph. Well, let's just take a moment and look at what we've got here. We've got an idea of what our graph of our original function looks like. It's got a peak here in the middle. So we know it's one of these two here. Peak, peak. This is a valley. So we don't want these with valleys. Now, how can we decide which one to choose? Well, we found a point on the graph at 0, -5. 0, -5 is down here. So we know we want graph D. Any questions on this? So that was number 11. I have a couple where I wanted to make a comment on. Let me just take a look at that. So on 12, you see you've got a quotient. You definitely want to use the quotient rule to find the derivative here. And let's just see. So I use the quotient rule. I got down to this. And I simplified. I got down to this. What you will notice is this entire denominator here is always positive. You can take any real number and square it. The worst case scenario you're going to have is 0 squared, which is 0, plus 2, which is 2, and then square that to get 4. That's the worst case scenario. The denominator is always positive. Why do I say that? Because then you don't have to set the denominator equal to 0 to find out when it's actually, for what axis make it 0, because those would be critical numbers. So your denominators here is not going to give you any critical numbers. That's why this is very important that we look at this. So the only place we need to look at here is taking the numerator and setting it equal to 0, which is what I did here. Solve for x, divide both sides by -24, x to 0 divided by -24 is still 0, and we just get x. And then you can go about your doing the problem just like we did before. So that would be 12 and 13. So just let me give you a quick lowdown on 13. It's asking for you to determine the X values, which are critical values, and really just understand why. Critical values are where you have critical values where you've got relative extreme points. So you find the critical numbers when you take the first derivative. That if you find those and you actually prove that you have a relative extreme point, you're talking about a relative minimum or a relative maximum. Now, critical numbers are only candidates for relative extrema. But in this problem, you want to look at it the way, what is the idea of a critical number and which X values are critical numbers? This is the original graph. So if you remember, critical numbers are the only candidates for relative extrema. So if you have any relative extrema, there must have been a critical number, because the critical numbers are the only candidates for relative extrema. So you want to just state right here in A down here, you want to find all of the X's here that are associated with a relative extreme point. In other words, there's a place where it changes from increasing to decreasing or decreasing to increasing. So for instance, at X sub 1 here, this changes from decreasing to increasing. So X sub 1 is a critical number. X sub 2, there's no change from increasing to decreasing or decreasing to increasing. It's totally increasing through here and only increasing. There's certainly no change. So X2, I did not include in this list at all. Let's see, X3, that's a good one, and we'll stop there after that. At X3 right here, there's a change from increasing to decreasing. So that is a critical value. It's a candidate for a relative extreme point. In this special case, it's a relative maximum. So X3, you do want to include in your list of critical values. And just one more over here, X sub 9 is right here. There's no change from increasing to decreasing. It's totally increasing through here. So X9 I did not include because there is no critical number with that, because there's no change from increasing to decreasing or decreasing to increasing. There's no relative extreme point there. Any questions? So sorry to keep you over a little bit. Very sorry about that. Thank you for being attentive, but before I let you go, I quickly have to just finished what I wanted to say. I need to quickly get your attendance. So I'm going to take a screenshot there. So I hope you all have a good day. I finished this assignment, so please work on it and bring your questions on Wednesday if you have any questions. And I wish you the best and take care. That's all for now. I will see you in a couple days. And if you want to reach out to me in between, feel free. Bye for now.
Bye.
Bye.